So we're going to pick up where we left off before spring break. Before spring break, we were talking about some different ways of proving triangles congruent. So I want to pick up from there and then move on to some triangle similarity. So this is the end of the PowerPoint that we were using before spring break. I just put a couple of slides up here as reminders of what we had done back in the good old days before we left. So sort of recapping triangle congruence theorems. There's three different triangle congruence theorems that we had looked at. The first one was side, side, side. So if three sides of one triangle, and maybe I'll mark them like this, 1, 2, 3, they could be congruent sides. In this case, no three sides of that triangle are congruent, right? We call that a scalene triangle. Three sides of one triangle have to be congruent to three sides of another triangle. And they don't have to be in the same orientation, right? I could mark them off three sides, one mark, two marks. These two triangles are still congruent because three sides of one triangle are congruent to three sides of the other triangle. All right, we also have the case of side angle side. So if I draw myself a triangle, two sides and the included angle of one triangle are congruent to two sides and the included angle of the other triangle. And again, I could have these triangles in a different orientation. The important thing is that the congruent angle has to be between the two congruent sides. It can't be down the bottom. It can't be over on the other side. It's got to be between the two congruent sides. Now, what's interesting about the third case is the case of hypotenuse leg. Remember that we said we couldn't use angle side side. We couldn't use side side angle unless we knew that the biggest angle and the biggest side were opposite of each other. Now, in a right triangle, we know that that's the case because there's only one 90-degree angle and there's only one hypotenuse, and they have to be opposite each other by definition. So if the hypotenuse and one leg are congruent to the hypotenuse and another leg, then the two triangles are congruent. So it could look like this, or it could actually look like this, right? Here's one case. Or maybe you want to mark off the bottom one as congruent. All right, so there's your right angle, congruent side, that leg. So it doesn't have to be one leg or the other leg, but it has to be consistent between the two of them. Hey, hopefully that makes sense. Let's try now perpendicular bisectors. Right? We had talked before we got to perpendicular bisectors about triangle congruence proofs, and we had done a proof that looked like this. Okay, we had two sides here that were given as congruent to each other, and then we were, well, that's weird, there we go. I had given angles down the bottom that were congruent to each other, right, because they were both right angles. And we had added that segment in the middle, right, that was congruent to itself by the reflexor property, and we'd written out a whole nice two-column proof based on this, and had concluded that therefore these two triangles had to be congruent to each other, right? Putting the letters in the right order, it was ABC, it was DBC, those two triangles were congruent to each other. And we had come up with another term while we were doing that, and that is that this segment here, BC, is actually the perpendicular bisector of segment AD. Why? Because once the two triangles are congruent, that means all parts are congruent. So this segment down here, right, that little segment down the bottom, is congruent to this little segment over here. So the two segments are congruent to each other by a term that we call CPCTC, corresponding parts of congruent triangles are congruent. That means that that segment BC is perpendicular to AD. It also bisects it, right? Bisect meaning it divides it into two equal parts. So therefore, it is what we call the perpendicular bisector. Now, you cannot bisect a line, right? I can't say, here I have this line that goes on forever, and I'm going to find the middle of that line. Now, I mean, it looks like that's the middle of the line. Remember, that line is just a little piece of something that goes on forever in both directions, so I can't bisect a line. I can bisect a segment, right? If that's the endpoint of one, that's the other endpoint. So I could actually measure it out, and I could find out, let's say that that's the middle of the segment, and then I can have a perpendicular bisector of the segment. Now, the perpendicular bisector itself can be a line, right? It just has to be perpendicular to and intersecting at the midpoint of that segment, and now it's the perpendicular bisector. Now, there's actually a couple of things that are true about the perpendicular bisector. One of them is that if you have a point that's on the perpendicular bisector of a segment, then that point is equidistant from the endpoints of a segment. So this point over here this is the same distance this way as it is that way. And if you go back to that triangle proof that we just did, you'll notice that that really is the same concept, that I end up with a length here that's the same as a length there because those two triangles are congruent. It also works the other way. If you have 2 points that are equidistant from the endpoints of a segment, so like here's 2 points equidistant from the endpoints of a segment, suppose I had another point down here, and these two distances were the same. If that's the case, then that segment that I have is the perpendicular bisector. So if those two things are the same, let's mark them with 3 marks because I already used 2. And then we'll mark this one over here. If these two lengths are the same and those two lengths are the same, then I know that that thing that I just drew is the perpendicular bisector. And that's what's covered over here. These are two different versions of the same theorem. One is that if a point's on the perpendicular bisector, it's equidistant from the endpoints. The other one is that if I have 2 points, each equidistant from the endpoints, then the segment that joins those 2 points determines the perpendicular bisector of this segment over here. All right, lines aren't straight, but I'm writing on a tablet, so we'll try to make do the best we can. All right, an isosceles triangle has base angles that are congruent. The base angles are the ones that are opposite the congruent side. So if I have an isosceles triangle means at least 2 congruent sides. So if I have an isosceles triangle, it's this side and that side, let's say, that are congruent to each other. Then these two are the base angles. The base angles are the ones that are opposite those congruent sides. So if you follow across, right, here's the angle, there's a side that's opposite the angle, here's the other angle, then there's a side that's opposite the angle. So in an isosceles triangle, base angles are congruent and opposite sides are also congruent. That's what an isosceles triangle is. Now, in an isosceles triangle, the altitude goes from the vertex and is perpendicular to the line containing the opposite side. Now, we use that language very specifically. In here, well, it looks like there's only one line that contains the opposite side. But we will see other cases where you can draw altitudes that are not connected directly to one of the sides of the triangle. So there's one of those altitudes. It extends from a vertex as perpendicular to the line containing the opposite side. So altitude means perpendicular. So if you cement those words in your head, altitude, perpendicular, and then of course perpendiculars make right angles, so we know those as well. All right, in an isosceles triangle, the median, the altitude, and the bisector of the non-base angles are all the same segment. Whoa, there's a lot of stuff in there. All right, so the median divides the segment into 2 parts, right? So this segment here and that segment there are the same. That's what makes that segment the median. The fact that there's a right angle makes it an altitude. Now, this thing does one other piece. Up on the top here are 2 angles. If I have an isosceles triangle, it turns out that these 2 angles up here actually have the same measure. And that's why this one segment, again, specifically in an isosceles triangle, that one segment serves as the altitude, right, perpendicular. It serves as the median, meaning it divides it into 2 equal parts, and it serves as the angle bisector of the non-base angles, right? That angle up at the top is not a base angle. One base angle is here, the other base angle's on the other side. They're all the same segment. Now, this last thing here says that every triangle has 3 altitudes, but not all of the altitudes have to be inside the triangle. So let's see if I can switch boards for just a second. Here we go. So let's take a look at a couple of cases where we might have altitudes that are outside the triangle. All right, here's the triangle. And if I said, draw me some altitudes, you could draw me an altitude that goes like this, right? Altitude means perpendicular, so there's a segment that's perpendicular. But there's actually 2 more altitudes in this triangle. One of them, and I mean, there has to be an altitude from every vertex. So what if we extended this segment over here and then dropped an altitude from this vertex perpendicular? And that's why the definition says perpendicular to the line containing the opposite side. Because the altitude that I drew is not actually perpendicular to one of the sides of the triangle, right? The blue side ends over there. It's perpendicular to the line containing the opposite side. Now, bonus question, where's the third altitude in this triangle? Well, the third altitude results from extending the other side. So suppose I extended this side over here, right? Extend that side over there. That's the one vertex I haven't used yet. There's my third altitude. So this triangle actually has 3 altitudes. Every triangle has 3 altitudes. Some of them are nice and they're all in the middle of the triangle, but not always. So you may have to go from the vertex perpendicular to a line containing the opposite side, and you may have to extend those. Now, if you get a little confused how to draw them, just draw yourself a triangle and make sure that you have 1 altitude from every vertex. So you notice I got 1 altitude from the vertex up here. That's the one in green. 1 altitude from the vertex down the bottom. That's the one in red. That's the one that goes through the middle of the triangle. 1 altitude from the vertex on the corner. That's the one that's in black ink. Okay, so 3 altitudes in every triangle, 1 from each vertex. All right. Circumscribed polygons. If you can draw a circle around a polygon, every vertex lies on the circle, then you can say that the circle is circumscribed about the polygon, and the polygon is inscribed in a circle. So let's see if I can draw a very simple one over here, right? If I have a circle, if I have a circle and I can draw this polygon so that every vertex touches the circle, then the circle is circumscribed about the polygon because that's the one on the outside, and the polygon is inscribed in a circle. So my question was, can you both inscribe a triangle in a circle and then inscribe a circle in a triangle? Right? Inscribe a triangle in a circle and then inscribe the circle in the triangle. Well, you might actually want to start with the other direction first, right? So you might want to start by inscribing the circle in the triangle. All right, so inscribe the circle in the triangle. This is not going to be perfectly round, but we'll give it our best shot. All right, so inscribe the circle in the triangle. And now, can I inscribe a triangle in that circle? Sure, I can. Well, it looks like I can. There we go. 1, 2, 3. So I've got my triangle in a circle, and I got my circle in a triangle. Here, let's give this one more shot. Here. All right, so I've inscribed my circle in a triangle, and I've inscribed my triangle in a circle. So I can do both. So it says every triangle can be inscribed in a circle. Not every quadrilateral can be inscribed in a circle. Only if opposite angles are supplementary. All right, so I can inscribe a quadrilateral in a circle only if the opposite angles are supplementary. So here is a case of a quadrilateral that can be inscribed in a circle, in part because I cheated and I drew the circle first. All right. So if this angle here and that angle down the bottom add up to 180 degrees, then I can inscribe that in a circle. Why? Because each of those angles are half the intercepted arc. So the one angle up at the top, let's say, intercepts an arc that goes from here all the way around. And the other one intercepts an arc that goes from here around there. So the two of those add up to 360. Well, if each of those angles is half the intercepted arc, half of 360 is 180. All right, so they are supplementary. All right, let's take a look at a couple of other triangle congruence theorems. So we had done side, side, side. We had done side, angle, side. We had done hypotenuse, leg. This one is angle, side, angle. Now, angle, side, angle, notice the order that it's written in. Angle, side, angle. Two angles and an included side of one triangle congruent to the corresponding parts of the other. So angle, side, angle. The side has to be between the two angles. Look at the way that it's written up here. Angle, side, angle, with the side in between the two angles. So if that's true for one triangle, and then you have a similar case for the other triangle, right? Two angles in the included side. And again, right, the orientation doesn't have to be the same. It just has to be corresponding pieces, right? Two angles and an included side of one, two angles and an included side of the other. Then the two triangles are congruent to each other. So can we use that to prove triangle congruence? Let's give it a shot. Ooh. Look how fast I'm typing that out. So I've got a midpoint of a segment, and I want to prove that those two triangles are congruent. So you might want to copy that down, because I think the only way I'm going to do this without squeezing it in the corner is by opening up my whiteboard and doing the proof that way. All right, so you might want to write this down somewhere, that n is the midpoint of UC. The two angles are congruent, so angle U in the corner over here and angle C in the corner up there are congruent to each other. If n is the midpoint of UC, then eventually I'm going to be able to conclude that those two segments there are congruent to each other, and I'm trying to prove that the two triangles are congruent. All right, you got that somewhere? All right, so let's draw this out here. We've got a set of triangles that looks like that. We got F up here, U, N is in the middle, C is up at the top, A is over here, and we need a two-column proof. So we need statements and we need reasons. The first thing is that we were given angle U is congruent to angle C. So I'm ready to start with the easiest part of this proof. Angle U is congruent to angle C. Why? That was given. If you want to label these as statements and reasons, we can. Right? Maybe after a while you get used to it and you don't need to write that every single time. So angle U is over here. Angle C is over there. All right, the second thing we were given is that N is the midpoint, and it matters what segment we're talking about, right? Because it looks like N could be the midpoint of two segments, but actually it's the midpoint of UC. Okay. And again, that was given. Now, depending on how accurate you want to be, do you want to be completely precise? Do you want to give just general reasons? I need to find out some reason that UN and NC are congruent to each other. They are, right? Because I know what a midpoint is. So for right now, I'm going to write UN is congruent to NC, and I'm just going to write the definition of a midpoint. Now, if you were going pretty in-depth in this, if you're going to an honors class or something, you would probably write out that a midpoint is a point that divides a segment into two congruent segments. But for now, let's just agree that we know what a midpoint is, and we'll put that out like that. So now I've got two pieces, but that's not enough to prove two triangles congruent. I'm going to need a third piece of information here. And what I'll do is I'll look at these two angles in the middle here that are actually congruent to each other, and I'll mark them off as congruent. Now let's be accurate. It's angle FNU congruent to angle CNA. Do you see why they're congruent? They're vertical angles. So if two angles are vertical angles, then they are congruent. I'm just going to run out of space. There we go. All right, so now look, I've got an angle, and a side in the middle here, an angle, and a side in the middle there. So therefore, the two triangles are congruent. So is triangle fun? Of course, it has to be triangle fun. And then the other one starts up on the top. So it's triangle ACN. Those two triangles are congruent by angle, side, angle. Two angles in the included side of one triangle, two angles in the included side of the other triangle. All right, let's go back to our triangle congruence proofs over here, because we've got one more, just one more, way of proving two triangles congruent. And that is angle, angle, side. And so angle, angle, side says if two angles and the non-included side. So I think this is the first one that doesn't include the side in between them. So two angles and the non-included side of one triangle looks like what? Two angles and the non-included side. Not this one, that's the included side. Non-included side. Here's where angle, angle, side gets tricky. All right, here's one. What if I drew another triangle like this? and I drew out this, and that, and that. And I said, are those two triangles congruent? The answer is no, because, look, here the congruent side is opposite the angle that has 2 marks. Here the congruent side is opposite the angle that's got 1 mark. So these two triangles are not congruent because I flipped them around on you. All right, so just be careful that the congruent side is opposite the same angle in both of them. All right, so let's take a look at this one. Look, it spells the word math. I'm sure it spells something else too. Thma. So AH bisects angle MAT. So let's just draw on this for a second. Angle MAT is this angle up here. So if AH bisects it, then it divides the angle into 2 congruent angles. Angle M and angle T were given as congruent. So this angle here is congruent to that angle up there. And I'm trying to prove the 2 triangles are congruent. Well, I've got 2 of the angles. I can't use angle side angle because I don't know anything about AM and AT. Right? I don't know if this one is congruent to the one on the other side. So what else can I figure out? I can figure out that AH is congruent to itself, right? That's reflexive. And now do you see that I've got 2 angles and a non-included side congruent to the same 2 angles and non-included side on the other one? Therefore, those 2 triangles are congruent. So if I were going to write it out, I would end up with after the given information, right? So here, let's see if I can squeeze this up here. I'm going to let you fill in the given information, and then I'll fill in that angle. Can I get rid of that line in the middle here? Angle MAH is congruent to angle TAH. And I'm going to put this as definition of angle bisector. And then I'll put in AH is congruent to itself. That's reflexive. And then my last thing will be to actually put the conclusion in there. So triangle MAH congruent to triangle TAH. And that is what? 2 angles and a non-included side. So 2 angles and a non-included side. So I'll let you fill up the givens up at the top. And that's how those 2 triangles are congruent. All right, let's do a couple of more examples, and then we'll wrap this up, and we'll move on to a second video that's got some similarity issues in it. All right, so show that these 2 triangles are congruent. If it's hard for you to see them drawn out like that, draw them separately and orientate them the same way. Right? So if I draw out triangle, let's say ABD, here's angle A, there's angle B, there's angle D. So angle ABD is the 70-degree angle, and ADB is the 50-degree angle. So I want to draw this now so that they're lined up in the same way, so that in the other triangle, the 50-degree angle is down here, and the 70-degree angle is up at the top. So it looks like I should do CB up at the top, D down the bottom, and then does that make sense that CDB is 50 and CBD is 70? Yes. So now do you see that they're lined up in the same way? So I've got 2 angles, and what else? Well, this side over here is congruent to that side over there by the reflexive property, right? BD is congruent to BD. That's reflexive. And so the 2 triangles are congruent. Triangle ABD is congruent to triangle CBD by what? Angle side angle. All right, let's try another one. Again, I would take these 2 triangles and separate them if they're hard to see the way they're written. So if I draw out, I'm going to pick DEC because that's the easiest one for me to see first because I can see where that right angle is. So D is up at the top here. E is the right angle that's at the bottom. C is over here. How does the other one go? The other one starts with an A, B is the right angle, and C. So there's A, B is the right angle, and then there's C. All right, so CB and EC are both 3, so I'm going to mark those two as congruent to each other. I see the two angles at the top at A and D are both 30 degrees, so I'm going to mark them as congruent to each other. And now when I do that, what do I have? I have a case of a right angle, one leg, angles up at the top. How do I know that those two triangles are actually congruent to each other? It's not side, side, side. What else could it be? Could it be angle, side, angle? Do I know that DE and AB are congruent to each other? No. But I do know that the angle down the bottom over here is shared by both of the triangles. So the angle C that's over here is the same as the angle C that's over there. Now the two triangles are congruent by angle, side, angle. You realize there's an extra piece of information in this problem. Those two angles up at the top that are congruent actually are not even really necessary. So once we have angle C congruent to itself by the reflexive property, then the two triangles are congruent angle, side, angle, right? Every right angle is congruent to every other right angle, so we don't have to worry about that. All right, one more. So opposite sides in a parallelogram are congruent to each other. Our goal is to show that the diagonals of a parallelogram bisect each other. So if we look at the parallelogram the way it's set up, right? This angle and that angle are congruent to each other because the two parallel lines make alternate interior angles congruent. Same thing with that angle up on the top and that angle up at the bottom. So in a parallelogram, I know that opposite sides are congruent, so that side and that side are congruent to each other, which actually then means that this triangle on the top here and this triangle down the bottom there are congruent to each other by angle, side, angle. And that means all the corresponding parts are congruent too. So opposite that double angle, that side's congruent. And now look at this. I don't want to use a single mark because I've already used it before, so I'll use a little B. There we go, a little V for like birds. And now look, the diagonals bisect each other. So once you fill in the property of a parallelogram that opposite sides are congruent to each other, then you've shown that the two triangles are congruent. And it actually is true that once you've shown that, then corresponding parts of congruent triangles are congruent, which explains how I get those things that have the two marks and the marks on the other side. All right, let me just check one other thing. Yes, okay. All right, so that should be good. That takes care of everything from that PowerPoint that we didn't finish before spring break, and then we'll worry about the similarities in a minute.